Hi everyone. In this video, we're going to talk about conditional probability. Conditional probability means that you have some condition that has been given to you that has already been met, and then you're asked to find a probability based on already knowing that condition has happened. The kinds of problems that we have been doing, such as when we talked about dice rolls and what's the probability of rolling a 7, for example, those were more simple probabilities. In other words, there was no extra conditions that were being met in those kinds of problems. So conditional probabilities, to give you a similar example, would be like if I said, what's the probability of rolling a 7 given that I rolled an odd number? So I'm now telling you that I just rolled these dice, like I'll roll these dice right now, and I just rolled an odd number. So what's the probability that it's a 7? So now the condition is that I've rolled an odd number. So you know for a fact that it's an odd number. So what's the probability that it's a 7? Well, there's 36 total outcomes with all of the dice, and there's the same number of even and odd outcomes. So if you cut 36 in half, you get 18. And so the probability of rolling a 7, given that I know I just rolled an odd number, would be 6 out of 18. So that conditional probability, it cuts your sample space to be smaller because there's a condition that's already been met. Okay, so that was a quick example using dice that I don't actually have written up here, but I'm hoping that that starts to open up your mind about what a conditional probability means. So this is the notation that we use in mathematics to represent a condition. So this shows the probability of A given B. So that's just a vertical line. And you read that as given. So it translates to mean given. So the probability of A given B means that the probability of event A occurring given that event B has already happened. So that means we know for a fact that B has already happened. Notice it's a little bit odd. This means that B must have happened first. So the thing that happened first, we write second in this notation. So it took me some time as a first-time student to get used to that mentality. So that's the first concept I want us to understand about conditional probabilities. The second idea is to know how to do problems where you're asked what's the probability of two things happening. It could be two or more things, but we're just going to focus on two things in this video. So the probability of A and B happening, remember that notation means and. I'm just going to add that right below here. This means and. So the probability of A and B happening means that B must have happened. So you find the probability that B happens, and then you just multiply by the probability that A also happens, but given that B has already happened. Okay, so now we know two notations are written on here to help us become more familiar with the mathematical notation. Okay, so let's look at an example to really unpack this concept. Suppose that you draw 2 cards at random out of a standard deck of 52 cards. What is the probability of pulling a king and a queen? Okay, so pretend I shuffled these and I pulled one card. So I pulled a king. Now I put them like that on purpose, but pretend that this was random. So what's the probability that I pulled a king and then a queen? So that is the question. What is the probability that this happens, that I just made happen, but what's the probability that it happens by chance if they were shuffled? Okay, so let's see. To find the probability that both things happen, that means the probability of a king and a queen happen. So that's my shorthand notation for both of those things happening. Okay, now it technically doesn't matter which one you pull first because there's 4 kings and 4 queens in the deck, but it says pulling a king and a queen, so let's just assume you pull the king first and then the queen. And so that means you need the probability of a king happening first, and then times, I already think I wrote this wrong, but let me finish it out. The queen given the king has happened. Okay, no, I wrote it correctly, but you could do it both ways, whether the queen comes first or the king, it'll be the same answer. So what this is saying is this is find the probability that you pull a king on the first draw, okay, that happens first, and then multiply that by the probability that you pull a queen given that you already pulled the king, So let's do that right now. What's the probability of pulling a king out of a standard deck of 52 cards? Now, if you're not familiar with cards, it helps to know all of the cards in a deck. So I printed out this picture, and it shows you that there are 4 of every number. There's also 4 suits. So their suits are hearts, diamonds, spades, and clubs. I guess I should point over here, hearts, diamonds, spades, and clubs. There happens to be 13 cards in every single suit because there are 13 total numbers. And so you can see that there are 4 kings and there are 4 queens. Okay, so maybe we'll just stick this up here momentarily so that we can all see it and refer to it. Okay, so, oh, well, you might not be able to see it. It's a little small, but I'll refer to it. So the probability that you pull a king on the first card is 4 out of 52 because there are 4 kings in the deck and there are a total of 52 cards. So that's probably that a king happens first. And now, if you want to know the probability that both things happen, a king and a queen, you want to know the probability that both things occur, the king must have come first, and then that card is removed. So now, what's the probability that you pull a queen next? Well, how many queens are left in the deck? There's still 4. And how many total cards are left in the deck after you remove this king that you just drew? There's now 1 less, so there's 51. And then you just multiply these. All right. And the reason why we're multiplying is because of all the different combinations, because I didn't have to pick this king in particular. It could have been any king. So I could have chosen this king first instead of this one. Or I could have chosen this king first instead of either of these, right? So why are we multiplying here? Because the same reason why we multiply when we do combinations and permutation problems. You're doing a counting problem here. You're counting how many different combinations are there for drawing a king and then a queen. And since there are 4 kings and 4 queens, you got to match up each of those with each other. So that would be 16 total combinations. And because you're drawing 2 cards, you have to match all the possibilities where you could draw 2 cards, any 2 cards, and that's your denominator. So 52 times 51 is 2,652. So that's the total number of combinations for drawing any 2 cards, and there are 16 total possible combinations for drawing those 2 specific cards, a king and then a queen. Okay. And if you want that as a decimal, you could always divide. So I got about 0.6%. Okay, so this is roughly 0.6%. Okay, now I'm going to connect this to some of the problems that we have done in previous videos to make sure that you really understand what a conditional probability means. I'll take this down so that you can see. So if I asked you the same exact question, but I changed this to say, suppose I draw 1 card. So if I only draw 1 card, what's the probability of pulling a king and a queen? So now that's saying if I only pull 1 card out of this deck, what's the probability that I pull both a king and a queen? And the answer is 0. There is no such card that is a king and a queen. These are mutually exclusive events. You can't be both a king and a queen. However, if I asked you, what's the probability of pulling a king and a spade? Well, now those are not mutually exclusive events because there is such thing as a card that is both a king and a spade. Now, there could be more than one if you're talking about a different problem, but in the context of cards, there is only 1 card that happens to be both a king and a spade. So if I asked you the same question, but changed this word to spade, where what's the probability of pulling both a king and a spade, the answer would be 1 out of 52. Because there's only 1 card that would be in the intersection of that Venn diagram that would include kings and spades. Okay. So that kind of ties us into the difference between the problems we did before and this new idea of a condition. So a condition means two things are happening. So that's why this number here, that was so critical, that this said 2 cards, that you're drawing 2 cards. We could also remind ourselves of those disjunction problems that we did in the previous video by asking a similar question but changing this word to or. So I could change this back to drawing 1 card. So let's say you just draw 1 card. What's the probability of pulling a king or a queen? Okay, or a queen. All right, so now the probability of doing either a king or a queen. So probability of king or queen, that's that union notation that we studied. That means we need to know the probability of pulling a king plus the probability of pulling a queen and minus the probability of pulling both in a single card, in 1 card. All right, so the probability of pulling a king, there's only 4 kings out of 52 cards. The probability of pulling a queen, there's only 4 queens out of 52 cards, assuming that you're only pulling 1 card. Okay, so this is not a condition anymore. Then you would subtract off any cards that are both kings and queens. But as we said before, these are mutually exclusive groups, so there is no card that's both a king and a queen. So the answer to this disjunction is 8 out of 52. Compare that to the answer to the conditional probability, which was 16 over 2,652. Okay, so again, this is a disjunction because just one thing is happening, and we're asking about what's the probability that one or the other happens. Okay, I'm going to hopefully try really hard now to demonstrate the difference between a condition written in one way versus a condition written in the other way. So here's what I mean. I'm going to grab all of the face cards in the deck. So the face cards are all of the jacks, queens, and kings. So if you're not familiar with cards, don't worry. I will give you that picture that I have right here. So you can use that when you're doing homework or taking tests. All right, so here are all the face cards. So I have a jack. I have 4 jacks. Here are the 4 queens. And here are the 4 kings. Okay, here's all the face cards in the deck. These are all the cards that have faces. No other cards have people on them. Okay, and so let's pretend like I'm gonna just shuffle these, okay? And I only have these cards, only the face cards. So if I asked you, I want you to think carefully about this. I'm just gonna pull a card at random. I'm holding a face card. We know I'm holding a face card because I told you we're gonna take only the face cards, and here's the rest of the deck that I have on the table. I'm holding a face card. What's the probability that it's a king? So if you know I'm holding a face card, and I just told you that the only face cards are jacks, queens, and kings, that means the total number of cards in my hand is 12. And how many kings are in here? Only 4. So the answer to that question, if I said I'm holding a face card, what's the probability that it's a king, is 4 out of 12. And I'm going to write that up here. So we have this as a second example. Okay, so example 2. If I am holding a face card, what is the probability that it is a king? Okay, in other words, this means what's the probability of me holding a king given that I'm holding a face card? It means this is what we know. We know I'm holding a face card, so what's the probability that it's a king? Well, because we know it's a face card, the denominator is 12. And because we know we're asking what's probably that it's a king, the answer would be 4. Okay, so 4 out of 12, which is a 33% chance, which makes sense because there are 3 different cards in here, right? So each one has 1/3 chance of getting drawn. What if I flip this though? So let's add one more example. So we'll call this example 3. We'll put this in red. Example 3. If I am holding a king, what is the probability that it is a face card? Okay, so this is still a conditional probability, but I have flipped the order now. So now I'm telling you that I'm holding a face card. No, I'm telling you that I'm holding a king. See, even I have to do them slowly. Okay, I'm telling you that I'm holding a king, and I'm asking what's the probability that it's a face card. Okay, so that means given that I'm holding a king, remember the thing you know that is 100% true comes second, or the thing that happens first comes second in the way that we write this, because we're asking what's the probability that I'm holding a face card given that it's a king. So I'm telling you I'm holding a king. So what's the probability that it's a face card? And you should say 100% because I know I'm holding a king. So the percentage here is 100%, or you can say the probability is 1, right? So probabilities are always decimals. So this is the same thing as equals 100%. This is the same thing as equals 33%, roughly 33%. Okay, so notice that if you flip the order, the answers are completely different. They have nothing to do with each other. So we need to pay extra careful attention to which one of these events are you given when you solve conditional probabilities. To drive this point home, we're going to do an example involving a table. So I'm going to erase this and I'll put example 4 up. Okay, so I'll leave that there in case we need it. All right, and I'll grab a marker. Actually, I'm not sure that we need that, so I'll give us more room. All right, example 4. Gabby owns lots of teacups. Okay, and we're gonna put a little chart for how many teacups she owns and what sizes she has, etc. All right, so she owns some small teacups and some large teacups. And she's got green teacups and yellow teacups. Okay, and then inside here we'll put how many of each she has. So I'll just make up some numbers. So let's say she's got 4 small green teacups. She's got 7 large green teacups. She's got 10 small yellow teacups. And then she's got 20 large yellow teacups. Sorry, she's got a lot of teacups. Okay. So let's ask a couple different questions here to really make sure we understand the difference between a conditional probability, a simple probability. I don't like that word, but it's more of a like the questions we did in the intro to probability videos. And let's put a disjunction as well. So we'll put a bunch of different questions here. So we'll put question A. If she draws or selects, I guess you don't draw teacups, you draw cards, you select. If she selects a teacup at random, what is the probability of selecting a green teacup? Let's do that. So that'll be part A. Then part B. If she selects a teacup at random, what is the probability of selecting a, let's go with small teacup, given that it's green? Okay, and we'll put one more question on here. Same idea. If she selects a teacup at random, what is the probability of selecting a small or green teacup? Okay, all right. So now we have 3 slightly different questions on here. All right, so let's go through each one at a time. So if she selects a teacup at random, what's the probability of selecting a green teacup? So this is one of the most simple questions that could be asked. Doesn't mean that it is simple, that's why I didn't like that word, but it's one of the simplest questions. So let me grab a red. So of just selecting a green teacup, you come up here and you look for what are all the teacups that are green, and so we should add on here a total. So if you're not given the totals for charts, then make sure you find them. So there's 11 total green teacups. I added 4 plus 7. And there's 30 total yellow teacups. And you could find the total number of small and the total number of large as well, but we don't need that for this question. We'll see if we need that later. So probability of her picking a green teacup, if she just picks one at random, is 11, because there's 11 total green. Out of the total of all the teacups, it looks like it's 41. So I'll put that right down here. Total of 41. So the probability of selecting a green teacup is 11 out of 41. And I'll just remind us how we did that. There's 11 green teacups out of the total number of all the teacups. Okay, so that was a simple question. If she selects a teacup at random, what's the probability of selecting a small teacup given that it's green? Okay, so this is a conditional probability because of the word given. Now, not all conditional word problems will use that word. They might say something like, if she selects a green teacup, and then you need to know that it's a condition because you're not selecting out of all the teacups, it's only the green ones. When you see this, given that it's green, that means you're only selecting from the green teacups. You might see things like, if we know that she chose a green, or if we're certain that it's green, or if she's holding a green teacup, like the way I did it with the face cards. So language is important, but don't only look for the keyword given. So just because you don't see the keyword given doesn't mean it's not a condition. It can still be a condition if certain conditions are met already. Okay, so in this case, we're only talking about the green teacups. So what I like to do is I like to, if I have a chart type problem, I like to hide the rows or columns that I don't need. So if we know that it's a green teacup because we're given that it's green, then we don't care about any of the yellow ones at all. So we're only talking about the green, and the green are right here. So we're only talking about this row. All right, so don't even look at the yellow and don't even look at the total either. So what's the probability that it's small given that it's green? All right, well, we figure out the total is all the green teacups, which is 11, and then we figure out how many of them are small, and there's only 4. Okay, so again, how do we do this? We found the small green teacups, and we divided by the total of green teacups, so all the green teacups. All right, and then the last problem says, if she selects a teacup at random, what is the probability of selecting a small or green teacup? That is a disjunction now because of the or. Okay, so it's not a condition. That means the denominator should still be the total, just like in the first question in part A. All right, so the probability of a small teacup, or you could use the union symbol, or green, and that should be, and you know what, I'm going to need more room on here, so I might have to erase and explain how I'm doing this so that you can see this a little better. So let me just erase the question. We can already see it's a small or green teacup. So if you don't already have it in your notes, go ahead and pause your video and put that question in your notes. All right, so the question is a small or green teacup. Let me use blue now. Okay, so the probability of small or green means we have to find, I'll put it down here, the probability of all the small ones plus the probability of all the green ones minus any of them that you just double counted. So minus any that are small and green. All right, so let's go ahead and find that. How many teacups are small? The total small is 4 plus 10 is 14. So 14 small plus the total number of green is 11. And then minus the ones that we just counted. We just double counted these 4 small green ones twice. We counted them once right here in all of the small teacups and once right here in all of the green teacups. So we just double counted that 4. So we have to subtract 4 so that we only count those 4 small green teacups once, not in both of these. All right, so if you do that, 14 plus 11 minus 4 is 21. All divided by the total number of teacups is 41, because this is not a condition, not a conditional probability. So notice the answers, only the conditional probability has a smaller denominator because of the condition. When you're given a condition, you know something is true with 100% certainty. So it reduces your sample space. It reduces the amount of things that you are selecting. Whereas in these questions, in part A and part C, these questions have the absolute total number of teacups because there is no condition being made in here. Okay, so those are the most common types of questions that you'll see involving a conditional probability. That should be enough to help you to make sure that you understand how to do these kinds of problems, but I'm going to do one more challenge question on here for fun. And you're probably thinking, like, we're going to do just a problem for fun? Yes, because it's challenging to think about, and it helps you in your life to think about whether certain probabilities are conditional or not, because conditional probabilities can be tricky. Okay, so here is the challenge question. So let's say that you are on a game show contest, and there are 3 doors. You've probably heard of this before. And I'll be the host. And so let's say I'm welcoming you to the show, and here are 3 doors, and behind one of these doors there is a car. And you get to choose any of these 3 doors that you would like. And if you choose the correct door that has the car behind it, then you win the car. Now the other 2 doors have nothing behind them, so if you choose them, then you don't win anything. So which door would you like to choose? Now I'm just going to answer for you. Let's say that you want to choose door number 2. I chose that because the middle door happens to be a pretty common choice among my students. So if you choose door number 2, what's the probability that you win? That's where the car is. Hopefully you're thinking it's 1/3, because each of these doors right now has a 1/3 chance of being the correct door that has the car behind it. So let's say that's what you stick with your door number 2, like that's what you chose, right? And now as the host, let's pretend I know where the car is, right? If I'm the host, I know where we have put the car. And I'm gonna pretend that you can see it with me, right? So come out of your participant role and come be the host with me for a moment. So if you're the host and you know that the car is behind door number 3, and your participant on this game show just chose door number 2, and you want to open up one of the other doors to let them know that the car is not behind that door, which door would you open up? Of course, you would open up door number 1. Okay, so let's say I'm the host and I say, okay, here's door number 1, and I show you like there's nothing behind it. Would you like to change your answer to door number 3? Or do you want to stick with your first guess of door number 2? And what should you do? Should you change your answer, or should you stick with door number 2? Does it matter? Do you have the same odds now? Is it a 50-50 chance now that you win the car? And the answer is no, it is not a 50-50 chance. Why is it not a 50-50 chance? Because I'm the host. I know where the car is for certain. With 100% certainty, I know where the car is. So there's a reason why I opened up door number 1 to show you that the car was not there. And it is because the car is here. So I have some restriction there. I cannot open up door number 3. I don't want to show you where the car is, because then if I ask you, do you want to change your answer? Of course, everyone would say, yes, I can see the car. So I want that door. So what happens is the probability that it's behind door number 1 is 0 now, which we all know. The probability that it's behind door number 2 is still 1/3 because that was the door that you chose. But the probability that it's behind door number 3 now is 2/3. And essentially what has happened is, because me being the host, I had to choose one of these 2 doors to open to show you that the car wasn't there. I was forced to show you this car. So the probability of the car, of this door, not this car, so the probability of the car being here gets transferred in a way over to this other door, because I couldn't show you this door because the car happens to be there. Now, you might be sitting there wondering, but I don't understand. It feels like it's 50-50. When would it be 50-50? When would it not matter? That's a great question. I had that question for a long time as a student. And the answer is, it wouldn't matter if this door got opened up by accident. So let's say I'm the host and let's pretend I don't know where the car is. So now we're not sure. The directors didn't tell me where the car is, so your guess is as good as mine. But let's pretend somebody that was backstage, kicked open a door, and door number 1 comes flying open by accident. Well, because that wasn't done on purpose, then now each of these doors, door number 2 or door number 3, has a 50-50% chance of you winning. So if the host then reacted to this accident and said, due to some technical issues, apparently the car is not behind door number 1. Do you want to change your answer? Well, now it doesn't matter. You have an even chance of selecting the correct door. Why is that? Because if a door opened up by accident, then 33% of the time, if the door kept opening up by accident, you had a 33% chance of opening the door that had the car in it. So if you're going to do it by accident, then there might be sometimes by accident that you'll show the participants where the car is. In this case, the situation that I explained to you, where the host opens up a door on purpose because I know where the car is and I don't want to show you where the car is, then this is a conditional probability and your odds are not 50-50. They are not the same because a condition has been met. The host knows where the car is, which also means the host knows where the car is not. And that is what she has shown you, that the car is not behind door number 1. So if that is your exact situation and you're on a game show like that and the host says, here's what's behind door number 1, do you want to change your answer to door number 3? Your answer should always be, yes, I'm going to change my answer. And you will double your chances. Here you had a 1/3 chance, now you have a 2/3 chance of being right. Now some of you are sitting there saying, but what if I was right to begin with? What if the car was behind door number 2 and I was right? Well, you had a 1/3 chance of being right. But if you switch your answer, you have a 2/3 chance of being right with door number 3. So, of course, none of these are 100% certainty. That's why they're probabilities, and that's why they're fun game shows to watch participants make decisions based on emotions and how they feel. I feel like it's behind door number 2. That's my lucky number. Instead of using math and probability to give yourself the best chances of being correct. If you have ever watched the movie 21, it's kind of an older movie now, It's a very entertaining movie, of course, to me as a math major. It is one of my favorite movies. And it's about a professor who recruits some of his students to come and play blackjack with him at a casino to win money by gambling. And he recruits his students by asking them this exact question in class. And so the main character in the movie answers the question. He answers it in about 10 seconds, but if you're interested, you can go watch that movie, and maybe his explanation might help to further your knowledge and deepen your understanding of conditional probabilities, and that there's a condition being met. Okay, I'm not going to ask you a question like this on a test. I just wanted to sort of push your thinking and challenge you. Think about what ways you might hear conditional probabilities in your everyday life, where somebody says, what's the probability that you're pregnant? And you go take a pregnancy test and it says 99% accurate. What does that 99% mean? Well, if you're wondering, that's a conditional probability. Okay, so pay attention to things in your everyday life, and you're welcome, or sorry that I pointed out that there's probabilities all around you every day.